So what we're going to talk about now is we're now going to be talking about something called the method of undetermined coefficients, or the method of annihilators. And what this is this is a way of solving non-homogeneous differential equations, and it plays a lot on the work that we did with homogeneous differential equations with constant coefficients. What we're going to need to start out with, though, is we're going to need to start out with talking about the annihilator. And the annihilator, again, is going to be very much tied to and connected to the work that we did previously with homogeneous differential equations with constant coefficients. So I'm going to review a little bit about that, and then we're going to talk about this annihilator, because we're going to use this quite a lot to solve these kind of differential equations. So now let's talk about what is an annihilator, and we're going to take an example. Let's say, for example, we have a homogeneous differential equation, d minus 3, d minus 2, y equal to 0. And we've already seen inside of our work with homogeneous differential equations that our solutions are going to be y equals e to the 3x, or c1 e to the 3x rather. Y equals c1 e to the 3x, and y2 is going to equal c2 e to the 2x. Okay? And so here's why this actually works. If we take d minus 3, d minus 2, and let's say we operate on this by e to the 2x. So without loss of generality, we can eliminate the scalar. It doesn't really matter because we're going to be taking derivatives, and scalars just can be pulled out of derivatives. So let's just consider e to the 2x. And if I take d minus 2 e to the 2x, just consider that. This is going to be the first derivative of e to the 2x, so that's going to be 2e to the 2x minus 2e to the 2x, and that equals 0. Right? That's why it's actually a solution to the differential equation, is because if you take the derivative of e to the 2x and subtract 2e to the 2x, you end up with 0. So now this piece here becomes 0, and this is now d minus 3, 0, and that is just going to end up equaling 0 because the derivative of 0 is 0, 3 times 0 is 0, so we just end up with 0. Conversely, if we switched it around, we could actually do this. We could take d minus 2 and d minus 3, okay? Same differential equation. We can actually do that because we're looking at constant coefficients, and we get now e to the 3x. We take e to the 3x, so now we operate on e to the 3x by d minus 3 first. So that's going to be d minus 3 e to the 3x ends up equaling 3e to the 3x minus 3e to the 3x, and that ends up equaling 0 as well. Okay? Then we take d minus 2, okay, and operate it on 0, and that just ends up equaling 0 as well. So in this case, all right, because we can actually move those differential operators back and forth inside of the differential equation, right, e to the 2x is going to end up zeroing out, okay, and e to the 3x is going to end up zeroing out right at the beginning, and then everything else ends up being zeros, okay, and that's just what happens. So what we say is we say this. We're going to say that d minus 3 annihilates e to the 3x. And we're also going to say that d minus 2 annihilates e to the 2x. Okay? So those are what we'd say the annihilators for e to the 3x and e to the 2x respectively. So if I have a function, if I have a function y equals e to the rx, okay, where r is a real constant, then d minus r is the annihilator for y. And you can see this, if I take d minus r, e to the rx, that's going to equal re to the rx minus re to the rx, and that equals 0. So that's the idea of how annihilators work. Annihilators work by basically going in and zeroing out a function, utilizing derivatives and essentially constants. So let's take a look at an example. Let's say, for example, I have y equals e to the square root of 2x. Its annihilator is going to then be d minus root 2, okay? And you can see that d minus root 2, and we'll call it this a of d. That's our notation for annihilator. And you can see that d minus root 2 e to the root 2x is going to be root 2 e to the root 2x. So if you remember our work with homogeneous differential equations, the you'll notice that essentially that our choice of an annihilator just came as a result of knowing that the solutions to differential equations that have like d minus 2 or d minus 3, they have functions in the form e to the, say, for example, rx. Now, what about repeated root annihilators? And so these are other ones that we actually find annihilators for as well. So let's consider something like this. Y equals x e to the 3x. Okay? Now, remember that we get a function x e to the 3x as a solution for repeated roots in P of R. So whenever we have P of R, right, if we have a repeated root, we're going to get a power of x e to the 3x. So in this case, right, remember that we're going to get, or rather, we're going to need something of the form d minus 3 squared, and then x e to the 3x, right? And if you see this, this is actually equal to d minus 3 x e to the 3x. So we'll start out with the first. The derivative of x e to the 3x is going to end up being e to the 3x plus x e to the, or 3x e to the 3x minus 3x e to the 3x. And so thus that ends up equaling e to the 3x. Okay, and so that's just d minus 3 x e to the 3x. Now, what do I have? I now need to operate by d minus 3 again, but I know that d minus 3 e to the 3x is just going to equal 0 by what we talked about before. So notice this is x to the first power. Okay, what we needed is, that means that we're going to need a second power, okay, on our real root annihilator. Okay, so like, say for example, we'll take another example. Let's say I have y equals, and it's x squared e to the 4x, or e to the negative 4x. How about that? E to the negative 4x. So I know that my annihilator for e to the negative 4x is going to be d plus 4. But I have x squared, so if you recall, no power is needed for the first power, and x is needed for the squared, so this is going to require us to have a third. D plus 4 cubed e to the negative 4x. And you'll actually see that we'll actually have the same thing happen as we had before. We'll reduce in power each and every time. You can go in and check it. Okay, let's do that. Or excuse me, it's x squared e to the negative 4x. So we'll do that. We've got d plus 4, and then d plus 4, because it's cubed, x squared e to the negative 4x. This is going to end up equaling then, first derivative is going to be 2x e to the negative 4x minus 4x squared e to the negative 4x plus 4x squared e to the negative 4x. Okay, and actually we're going to keep our d plus 4 squared. We'll operate on that. Those. And if you see this whole thing, we're going to just be left with 2x e to the negative 4x. So I've now got d plus 4, 2x e to the negative 4x. So I've actually lost one of my powers of x, which is exactly what I wanted to have happen. Now we'll operate again by d plus 4. So that's going to then be d plus 4. That's going to be this one left over. And then the first derivative of 2x e to the negative 4x is going to end up being 2 e to the negative 4x, okay, minus 8x e to the negative 4x plus 8x e to the negative 4x. And that thus is going to equal d plus 4, 2e to the negative 4x. Now notice the fact that it doesn't really matter what the scalar is in front, right? That scalar isn't actually going to make a difference. And again, that a lot of that just has to do with the nature of the derivative. We can actually pull the scalar out of the derivative, right? And that scalar is going to end up getting multiplied through for every single term. So like in this case, you could see that if we take the derivative of 2e to the negative 4x, we get negative 8e to the negative 4x, and then plus 4 times 2 So that's 8e to the negative 4x, and that equals thus 0. So we end up annihilating. And that works out really well for us. So that actually gives us another way of finding an annihilator. So if we get y equals x to the n e to the rx, the annihilator will be d minus r to the n d minus r to the n plus 1. Right? And you can see that in this case we had an x squared, so we needed the cubed. In this case we had the power of 1, we needed the squared. So we're going to get d minus r to the n plus 1, and that's going to be our a of d for y equals x to the n e to the rx. Give you just a quick example. Okay, let's suppose that we get y equals, okay, and we'll have x cubed e to the negative 6x. Then our annihilator, a of d, is going to end up equaling d plus 6 to the 4th power. And there's our annihilator. Okay. A note on these repeated root annihilators, okay, and this is actually kind of an important thing too, is that if I have an annihilator of the form, let's say for example x cubed e to the 4x plus x e to the 4x, all right, or some scalars along those lines. Notice that this is e to the 4x and this is e to the 4x, okay, and the highest power is a power of 3. So we've got the highest power is a power of 3. So what we've got here is we've got, in fact, our annihilator is going to be exactly the same as it would be if it was just this annihilator, if it was just this function here. So our a of d is going to end up being d minus 4, okay, d minus 4 to the 4th power. And the reason why that's the case is because at some point in time, x e to the 4x, actually after the second operation by d minus 4, x e to the 4x is going to zero out, okay? Because we're taking its derivative, right? So like, in this case, what you could think about is you could say, okay, if I got d minus 4 to the 4th, and I'm operating on x cubed e to the 4x plus x e to the 4x, what I can do is I could actually say, okay, this is actually d minus 4 to the 4th, x cubed e to the 4x, plus d minus 4 to the 4th, x e to the 4x. We already know that this is going to go to 0, and this actually, its annihilator is d minus 2 squared, is a of d for x e to the 4x. So after 2 operations on, d minus 4, not d minus 2, d minus 4, 2 operations by d minus 4, we're going to get this thing going to 0, so the last 2 are just going to zero out as well. Okay? So essentially, if we could actually write this, if we have an annihilator of the form, or if we get y equal to x to the n e to the r x plus x to the n minus 1 e to the rx, okay, and we'll add some scalars in here. So c1, c2, x to the n minus 1 e to the rx plus all the way down to just cn e to the rx. Our annihilator actually remains the same. A of d is still going to end up equaling d minus r to the n plus 1. Because these will all be annihilated by this term. So the last set of annihilators that we're going to look at are for functions of the form of cosine and sine functions. So for example, let's say I have a function y equals cosine of 6x. So what I want to remember is that, remember from the homogeneous differential equations conversation, that an annihilator of the form cosine 6x actually had a complex auxiliary polynomial. Okay, so it had a complex auxiliary polynomial, or an auxiliary polynomial with complex roots. Okay, and what we had was we had roots of the form in this case, r minus, and this would be 0 plus 6i, okay? And also r minus 0 minus 6i, okay? Because if you remember what we had from Euler's formula is that e to the a plus bi x would end up equaling e to the ax cosine bx plus e to the ax sine bx. Okay? So, given the fact that I have y equals cosine 6x, what I can see is I'm going to have that complex root. And in this case, b is going to end up equaling 6. That's why I put the 6i here. Okay? And a is 0 because there's no e to the e power here. All right? So my annihilator is actually going to look like this because I'm going to actually need the complex conjugate. So I'm going to have r minus 6i times r plus 6i. Right? That's going to be the polynomial. This is going to end up giving me r squared plus 36. And if I turn that into an annihilator, that's going to end up being a of d equals d squared plus 36. Okay? So what we need to do is we need to actually go back. We're going to re-engineer, right, the annihilator from the polynomial, right? Because it's a little less straightforward than the other two were. The other two were a bit more straightforward. This one is actually going to force us to, kind of think backwards, all right, in order to create, a complex or an annihilator that has complex roots. So let's take another example. Let's say, for example, I have y equals, and let's have it be e to the 6x sine 4x. Now, what I want to do here is I want to rewrite this. This is going to be my real part. Okay, so my root is going to be r equals r equals 6 plus or minus 4i. Okay, because 6 is the real part, 4 is the complex part. So now I'm going to take r minus 6 plus 4i, and I'll multiply that by r minus 6 minus 4i. Okay, because we're going to need we're going to need the conjugates here. And so this is going to end up giving me r squared minus, and this will be 6 plus 4ir minus 6 minus 4ir plus, and then this is going to be 6 plus 4i times 6 minus 4i. This ends up equaling r squared. This is going to be minus 6, but then I'm going to have a minus 4i and a plus 4i, so they're going to go away. So this is going to end up being minus 12 plus, and this is going to end up being 36 minus 4i squared. Or excuse me, minus 16i squared. Pardon me, 16i squared. Right, because that's a difference of squares right there. And so this ends up being r squared. Excuse me, and this is 12r. Sorry, there's an r there. 6r, and 6r. So this is 12r plus, and this will be then 36 plus 16. So that ends up being 52. So this is r squared minus 12r plus 52. And so that consequently, we're going to use that now to create our annihilator. So a of d in this case is going to equal d squared minus 12d plus 52 by just bringing back the differential operator. Okay? Let's do one more. Let's say, for example, I now have y equals, okay, and we'll have e to the negative 2x sine 3x plus e to the negative 2x cosine 3x. Notice in this case that the power of e is the same, and the power, and the coefficient in front of the cosine and the sine argument is the same as well. So we can actually use the same annihilator here. It's going to be of the form, our solutions, or our root is going to be of the form r equals negative 2 plus or minus 3i. So we'll just plug that into a polynomial. We're going to get r minus a negative 2 plus 3i times r minus negative 2 minus 3i. And this ends up equaling r squared. And then we'll get minus negative 2 plus 3ir minus negative 2 minus 3ir plus negative 2 plus 3i times negative 2 minus 3i. So this gives me r squared. The 3i's are going to cancel because I got a minus 3i and a minus 3i. So I'm going to be left with just the plus 4r. So this is going to be plus 2r plus 2r. And then this is a difference of squares now. So this is going to be plus, and this is going to be 4 minus, and this will be 9i squared. I squared is negative 1, by the way. So that gives me 13. So this is going to end up being r squared plus 4r plus 13. So my annihilator, A of d, is going to end up equaling d squared plus 4d plus 13. One last thing is that just like how we worked when we worked with the homogeneous differential equations with constant coefficients, we can actually have higher powers of the complex coefficients, or excuse me, our complex auxiliary polynomials. So like if, for example, we have something of the form y equals, and let's say x cubed e to the 4x cosine 2x, then what I know is that I'm going to have the base annihilator, and then I'm going to raise it to the 4th power because I've got an x cubed in front of the e to the 4x cosine 2x, right? The powers, the adding of powers works exactly the same for complex auxiliary polynomials that have complex roots as it does for ones that don't, okay? So in this case, I'm going to know that r is going to equal 4 plus or minus 2i. So I'm going to go out, I'm going to find so just to make things a little bit easier, we actually have an equation. You may have noticed how it kind of works. If our solution is of the form r equals a plus bi, okay, then the polynomial that we're going to get that's going to have roots of the form a plus or minus bi, excuse me, is going to be of the form, it's going to be r squared minus 2ar plus a squared plus b squared. Okay? And that ends up being the polynomial that we're looking for. So in this case, we're going to get r squared minus 8r plus, and then a squared plus b squared, so that's 16 plus 4, so that's plus 20. So r squared minus 8r plus 20 ends up being the polynomial that we're looking for. So my annihilator, A of d, is going to end up equaling d squared minus 8d plus 20. And then we're going to have to go in and raise it to the 4th power because because we've got the x cubed term in front of it. So we've got to actually raise it to a n plus 1th power. So our functions, if we've given particular functions, in summary, of the form y equals c e to the rx, then our annihilator A of d is going to be d minus r. If, on the other hand, we're given y equals c x to the n e to the rx, then our annihilator is A of d equal to d minus r, and we're going to have to raise it to a power because we've got that power of x. Or if we have our cosine or sine functions, ce to the ax cosine bx, or ce to the ax sine bx, then we're going to get A of d is going to equal d squared minus 2ad plus a squared plus b squared. Okay, which is basically, you know, going in and finding the polynomial that gives you these complex roots. In addition to that, don't forget that with the cosine and sine, we can also raise them to powers, right? If we happen to be adding in a power of x in front of the equation. And in addition, if we have other roots, right, or we have other other functions that have the same root, the same r, and smaller powers of x, we can continue to just utilize the same annihilator, okay? So basically we're always going to be going to that highest power of x, okay, in terms of the power for our annihilator, right? So that kind of completes what exactly an annihilator is and the different kind of examples that we see there.